right, so I can continue. So let's continue with lecture 4. Yes, so first, if the definition of mixed volumes was not very clear last time, today there will be almost absolutely no mixed volumes, so one can understand this lecture. Secondly, so Professor Tiwari will send my lecture notes, which I prepared for it. Will share them in some way. So the lecture notes up to this lecture, including this lecture. All right. So first thing today, I will state another inequality, namely the Minkowski inequality. Minkowski inequality. Then I will show how it implies the first and second Minkowski inequalities, so which I described yesterday. But then the most important part of the lecture will be the proof of this inequality, and this is a very beautiful proof. So there are two important things today. First is the formulation of this inequality. Then in the middle is something where one can relax a little bit, but then there will be time to wake up and listen to the proof of this inequality. So, but first, what is the inequality? So this time we take two convex sets K0 and K1 in RD. Be compact convex sets. So I don't say convex bodies, because what is a convex body? It's compact convex set with non-empty interior. This time I allow the interior to be empty, because the theorem is also interesting under this assumption. So for these two bodies, we define a family of convex bodies, K lambda, which is 1 minus lambda times K0 plus lambda times K1, and lambda is between 0 and 1. So this is sort of linear interpolation between the two convex bodies. When lambda becomes 0, then K lambda becomes K0. When lambda becomes 1, then K lambda becomes K1. And this is all as usual. So this is scaling, and this is Minkowski sum. Then the volume of K lambda, well, in fact, the dth root of the volume is a concave function of lambda. So somehow the statement is quite natural, so not that one can guess it easily, but the volume itself is something of degree d, right? So if you have a d-dimensional set and volume is of degree d, if you take the dth root, then it should be something, well, linear, but in this case it's not linear, it's somehow it's concave, so it's bigger than linear. Okay, let us look at some examples in order to convince ourselves that this can be true. But there is also equality condition, in fact. Equality condition is, so equality occurs in two cases. First, if dimension K of K0 and K1 is smaller than d, so that is if they are not convex bodies, if they have no interiors, and besides if they lie in parallel hyperplanes. So, and in parallel hyperplanes of RD. And second case is when K0 and K1 are homothetic. homothetic includes that they are parallel translates of each other, and it also includes homotopy with coefficient 1, so that one body is a point, the other one is anything. Homothetic. Okay, then that's the end of the statement of the theorem. Now examples. Well, first, in dimension 1, the theorem is practically trivial, because in dimension 1, any convex set is a segment, and linear combination of two segments is again a segment whose length is a linear combination of the length. Right? So length. So in this case, this is first root of the length of a segment. Well, somehow the length of our segment. And the segment depends linearly on lambda, and so this is linear in lambda. Equality. I mean, of course, so what does it mean, equality? There is no equality because there is, it is called inequality. But I mean, so the concavity is sort of inequality, right? And the equality is that the function is linear. So that's not equality, that's linearity. So this function is linear in one of the following two cases. That's what I mean. And yeah, so in this case, when dimension is equal 1, then there is linearity, and that's because any two segments, of course, are homothetic to each other. Two segments in a line are homothetic. Then second example, we take two segments in the plane, so d equal 2. Well, if these two segments are parallel, then one can see that the linear combination is again a parallel segment, and then the volume is just identically 0. So we are again in the linearity case, and it's because the first condition is satisfied. So we don't consider parallel segments. Well, we have already considered them, so we don't consider them anymore. So let me take two orthogonal segments. So some two special orthogonal segments. So one will be the segment from -1 to 1 on the x-axis, and the other one will be, let's make it one a bit bigger, and the other one will be -1, 1 on the y-axis. So this is k0, and this is k1. Then what is the linear combination? The linear combination is just a rectangle like that. So if one thinks a little about that, then one can see that that's the linear combination. So this is 1 minus lambda k0 plus lambda k1. So the function, so this square root of the volume of k lambda is equal in this case. So this is segment 1 minus lambda, rectangle 1 minus lambda times lambda. No, it's twice 1 minus lambda times twice to lambda. So we have 2 times the square root of lambda times 1 minus lambda. This is the function. Okay, so that's some calculus problem to show that it is concave, or for those who don't like formulas, there one can just make a simple transformation and to see that this is actually the square root of 1 minus some square. So the graph is in fact just half circle. So that's exactly the half circle. And this curve is concave. So it's half circle. Yeah, so without calculus, one can just use algebra and see that this is equal to 1 minus 2 lambda squared. Good, so these are examples to the concavity of this function. One remark, in fact, and this is somehow, so I'm sorry to say it, but actually convexity here is not needed. convexity of K0, K1 is not needed. The theorem holds also for non-convex sets, just for any compact measurable sets. But most applications of this theorem, they are in the convex geometry. On the other hand, well, from my point of view, they are in the convex geometry, but the inequality is also related to many other inequalities, and there is a survey by Gardner, so Richard Gardner, with 150 references, and it relates this inequality to many other inequalities. So in the notes, I give a reference to this survey. All right. So now there comes the less interesting part of the lecture, and so I will tell you when you should listen again. But still, so this is not interesting, but I want to explain that this theorem implies both Minkowski inequalities. Good. So just straight to the matter, consider the following function. F of lambda is equal our square root of volume. Yes, not square root, this root. So let me write it like volume of k lambda to the power 1 over d minus 1 minus lambda volume of k0 to the power 1 over d minus lambda volume of k1 to the power 1 over d. So what I have done, from my function for which I somehow know the concavity, now I assume that Minkowski is proved, right? So I assume Minkowski and prove something else. So from my concave function, I have subtracted some linear function. So therefore, this function is still concave. So by Minkowski, f of lambda is concave. Besides, why did I subtract? Why did I do that? I did that because now f of 0 is equal 0 and f of 1 is equal 0. F of 0 is equal f of 1 equals 0. But then if you have such a concave function, then its first derivative is non-negative. Its first derivative at 0 is non-negative, right? So this is a function like that. And so f of 0 is non-negative. And now if one computes this derivative, and so one has to spend some time, k lambda is such a linear combination, volume of this combination, so one encounters the mixed volumes, and this implies the first Minkowski inequality, which was what? So which was the area of the boundary. Well, no, that was not the area of the boundary. It was the isoperimetric, but there was this v1 to the power d is bigger or equal than v0 to the power d vd. So vd is the volume. No, yes, vd. So these are these mixed volumes of k0 and k1, and the index shows how much of k1 is mixed in this mixed volume. But here's the power d minus 1. But also, if one has a concave function, then the second derivative must be non-positive. second derivative at 0 is less or equal 0. And this implies the second Minkowski. Do I remember what it is? So it was v1 squared is bigger or equal than v0, v2. Yes. All right, so this is actually some lengthy calculation, but it gives exactly the two inequalities. And now I'm going to prove the Minkowski inequality. I remove that. So 4.3. So the title is Steiner symmetrization and Schwarz rounding. So these are the methods with which we prove the Minkowski inequality. So first we change the formulation. So we reformulate it in a different way. So we have this K0 and K1. Let us, for convenience, put them not in the same RD, but pull them apart. So let us use RD plus 1. So in RD plus 1, lift K1 to the hyperplane xd plus 1 equal 1. And K0 will remain in the xd plus 1 equal 0. So then we will have the following picture. So here is the plane xd plus 1 equal 0, and in this plane there lies the body K0. And that is the plane xd plus 1 equal 1, and here we have the body, or actually not the body, but the compact convex set K1. And I claim that if you take the convex hull of these two, then the sections by the planes xd plus 1 equal lambda are exactly these, so these linear combinations. So which is easy to believe, right? So if I take section by xd plus 1 equal lambda, then this section will be k lambda. So then the section of the convex hull of K0 union K1 by xd plus 1 equal lambda is k lambda. Good. Now let us do the following thing. So we have this convex, so sort of barrel, so some convex set with two bases. Now let us, in every hyperplane xd plus 1 equal lambda, let us take this k lambda and replace it by the ball of the same volume. So replace k lambda by the ball of the same volume, and centered at the sort of, so here is the xd plus 1 axis, and we will replace k lambda by a ball of the same volume and centered at the point on the xt plus 1 axis. So what we get is sort of body of revolution. So now it really looks like a barrel, so you know things to hold liquids. But why does it look like a barrel and not like something like that, not like this? That's exactly the formulation of the Brun-Minkowski inequality, because so these balls that we obtained, their radius is proportional to the dth root of their volume, right? The volume of a ball, it's radius to the power d, and then times some constant. Therefore, the concavity of that function is equivalent to the convexity of the barrel. So great. So what we have to prove in the Brun-Minkowski theorem. So this body of revolution. I mean, in high dimensions, it's not body of revolution because you cannot rotate around one. Well, sort of, you cannot rotate around one-dimensional axis in R4, but I will call it body of revolution. Well, you can rotate, but it's now, one can discuss the terminology very long. This body of revolution is convex. So that's the first important point in the proof. I mean, the point in the proof is that I have now shown that the Brun-Minkowski theorem is equivalent to the statement that this body of revolution is convex. And now I proceed to prove that this body is indeed convex. So the idea now is to replace this. In fact, so this procedure, this is what is called Schwarz rounding, replacing each section by the ball of the same volume. It is not clear that Schwarz rounding gives something convex. But there is Steiner symmetrization, which is so some simple operations, and it preserves convexity. So what we will now do, we will show that Schwarz rounding can be represented as a sequence of infinitely many Steiner symmetrizations. But first, I explain what is Steiner symmetrization. So, definition. Now let K in RD, well, somehow, now it's not in RD, but here now just to be somehow consistent, so this body I will denote by K tilde. So this body will be denoted by K tilde. So K tilde is this convex hull, and after this is the transformation of K tilde. K tilde is a subset of RD plus 1. Now I take K in RD, so which just something unrelated to that. So let this be a convex compact, and let H be a hyperplane. Then the Steiner symmetrization, Steiner symmetral of K about H. Well, somehow symmetrical for me is the result of symmetrization. Maybe that's not a very good word, but the result of Steiner symmetrization of K about H is constructed as follows. Let me draw a picture first. So this is K, and this is H. The picture is in dimension 2, but one can easily imagine anything in higher dimensions. What I do, I decompose H into segments, so into infinitely many segments orthogonal to H. And then I move each of the segments so that its midpoint goes to H. So H is still there, but now K becomes symmetric with respect to H, because each of these segments has the same length, but its midpoint is on the line H. And I guess I will not write description in words, so just move all vertical segments to the middle. What is obvious is that the Steiner symmetrization, so I will denote this result by St sub H of K, it preserves the volume. Because one can compute the volume by the integral, and the length of the vertical segments doesn't change, so the integral does not change. But what is more, and it's an exercise, if K was convex, then the Steiner symmetrization of it is also convex. All right. But then the idea would be, instead of doing everything at once, so taking this section and replacing it by the ball, let us symmetrize it in one direction, symmetrize it in the other direction, and so on. We know that under each, well, somehow we symmetrize the whole body K tilde at the same time with respect to some vertical hyperplane. And if we do it, then maybe slowly these bodies become balls, but it's not so obvious. Because, so here is another exercise. So if we perform the Steiner symmetrization with respect to coordinate hyperplanes, what do we get? So the result of consecutive Steiner symmetrizations about the coordinate hyperplanes is centrally symmetric, but not necessarily a sphere. So if you want, by applying Steiner symmetrization, if you want to get a round sphere, then we have to do something more. And so what we then do, so we take hyperplanes. So now, remember what do we want to do? We have sort of, so something, also how to do something which is not, rotation, which is convex, but still not a body of revolution. So we have this K tilde, which has K1 and K0 as its basis. And then we somehow, by Schwarz rounding, we make K1 to be a ball and K0 to be a ball, and each section here is also rounded. What we do now, we take hyperplanes H1, HD in RD plus 1. Here we live in RD plus 1. We take hyperplanes take vertical hyperplanes. We take hyperplanes which pass through the xd plus 1 axis, passing through the xd plus 1 axis, and such that their normal vectors span RD, and the angles between them are incommensurable with pi. Such that their normals span RD, and I say span RD, not RD plus 1, because the normals, all of them lie in the horizontal plane in the RD. Span RD and have angles between them incommensurable with pi, so that is irrational multiples of pi. So, and these skew and bad hyperplanes, this is what we need, because those good coordinate hyperplanes, they did not manage to round our body. Okay, but that's not, so we, how often should we symmetrize with respect to this hyperplane? So we take the sequence of symmetrizations, Steiner symmetrization, so STD composition, so on, ST2 composition, ST1. Apply it to K tilde, right? So which means first I symmetrize about the H1, then I symmetrize about the H2, then so on, I symmetrize about HD. That's still not enough, because I will need to repeat this composition several times. And then I claim that this sequence converges to the body of revolution. This sequence converges to a, so what I call body of revolution. If I prove this theorem, then the Blum-Minkowski theorem is proved, because I have reduced it to, yes, well, now one should make, so repeat those several steps. So because Blum-Minkowski theorem is equivalent to the statement that Schwarz rounding produces a convex body, then by this theorem that I am going to prove, Schwarz rounding is a limit of Steiner symmetrizations. And because Steiner symmetrizations, they applied to a convex body, they give out a convex body. So from these three steps, it follows that the Blum-Minkowski theorem is proved. But one has still to prove this convergence of the sequence. And this seems to be technical, but there are some beautiful tricks in there. So technique sometimes is also, in fact, beautiful, and one should learn, of course, these methods. So I will not have time to explain everything, but in this proof, so I give a sketch of the proof. Sketch proof for this theorem. So first, there is very useful theorem called Blaschke selection theorem. maybe I stated it already in the first lecture. So which said if one has a uniformly bounded sequence of convex bodies, uniformly bounded sequence of convex, well, compact convex. Well, in this case, they are almost. I will use bodies because the case when everything degenerates, it's anyway easier and it should be considered separately. So I have sequence of convex bodies, all contained in the same ball of radius on some big radius. For the sequence, one can choose a converging subsequence. Converging in the Hausdorff metric. And so this sequence is uniformly bounded. This is easy because if the body was already in a ball, then it will remain in the ball. So from this sequence, one can choose a converging subsequence. By the way, so the proof of this theorem, maybe it's easy. Well, so that's again something technical, but maybe it's easier to look at it in terms of the support function, because we have sequence of convex functions, and from the sequence of convex functions, one can choose a converging subsequence. But so one can choose a subsequence sequence which converges to something. But the question is, why is this something a body of revolution? And also, why does the whole sequence converges? Maybe it's not needed that the whole sequence converges, but in fact, it does converge. So not only a subsequence. So then the next technical ingredient is the following. So let me just think how much I should say. Okay, so so the question is now, why does this converge to the? So why is the limit a body of revolution? In fact, now one can even forget body of revolution and speak about the balls. So let me spend some time about this. So in fact, what we are doing here with these hyperplanes H1, HT, and RD+1, in fact, one can forget this D+1 dimensional body and look at every section just separately. So the section lies in RD, and in RD we have the hyperplanes, so which are intersections of these hyperplanes with RD. And these the hyperplanes, they span the whole RD and have angles between them incommensurable with pi. And what we want to show is that this sequence of symmetrizations now in RD converges to a ball, right? So if you prove it for every, so if you prove it for every section, then it holds for everything if there is some uniformity. But well, so in that sense, here one should ask, why is the limit a ball if you symmetrize across these skew planes? And also, why also the sequence converge? Why does the not only subsequence but also the sequence converge? For this, one can introduce a quantity which decreases each time when one symmetrizes. So when one does Steiner symmetrization, so which decreases with each symmetrization, and whose only minimum is the ball. Then, if such quantity exists, then it will follow that this limit is a ball, because the limit cannot be symmetrized anymore. So a quantity which decreases under symmetrizations. And whose only minimum among the bodies of constant volume. So for volume constant is the ball. So now more details about this quantity, and so this is the moment of inertia of K with respect to a point P. This is the, so denoted by mu of K, mu P of K. This is the integral of a K of the norm of x minus P squared dx. So the integral of the squared distances to the point P. And the moment of inertia of K with respect to a hyperplane H is mu sub H of K. This is the integral of a K of squared distances to H. So distance from X to H squared dx. Then there are two lemmas which I also leave as exercises. So first, oh, maybe one exercise. No, two exercises. So one is that the moment of inertia with respect to a point is in fact the sum of moments of inertia with respect to hyperplanes. Well, so these hyperplanes are not those that we have taken, but these are any pairwise orthogonal hyperplanes. So where H1, so HD are pairwise orthogonal hyperplanes. The second exercise is that if you symmetrize with respect to the hyperplane H, then the moment of inertia with respect to H decreases. So the moment of inertia with respect to H of Steiner symmetrization with respect to H of K is less or equal than the moment of inertia with respect to H of K. And the equality is if and only if K was already symmetric. But with respect to some, yes, was already symmetric with respect to H. Now, if one proves this, then one can already start proving the theorem that was here, that this sequence, since we have a converging subsequence, then it must converge to something symmetric with respect to H1, but also to something symmetric with respect to H2 and so on. So so let me write it also here. So from these two exercises, it follows that the limit of the converging subsequence K tilde I n. I mean, so if I introduce some notations, then this denotes what I want. So this limit is symmetric with respect to the hyperplane H1. If one proves that, then one also later proves that it is also symmetric with respect to H2 and H3 and so on. But since this H1, H2, H3, so they are not pairwise orthogonal, but they are really form some relational with respect to pi angles, the symmetry with respect to all these planes implies that the limit is a ball. And then with some more work, one can also show that the limit of this subsequence is also the limit of the whole sequence. Well, which actually is more or less clear, because if this subsequence converges to the ball, then so between these members of the subsequence there is something, but this something is symmetrizations of nearly balls. Yes, so if you become a ball, then after symmetrization you just get even more ball than you were. Okay, so then one can fill in here the details, but so I don't have time to do that because I want to save 10 minutes maybe to state some more stuff. But with this, actually with this, the proof of Minkowski is finished. But one bad news here is that with this method, I don't know how to prove the equality condition, the linearity condition. So that's so not clear how to derive the linearity conditions. By this method. There are several other proofs of Minkowski inequality which also derive the linearity condition, so that the bodies are homothetic. That's the only case when this function becomes linear. But this proof is, I mean, so good that it would be good maybe to add to it something. So in a book by Blaszke, there is a proof of the linearity condition, but only for some small dimension, dimension 2. So if somebody knows about a proof published elsewhere, or somebody can, by this method, prove also this equality, say linearity condition, that would be nice. I still have 10 minutes because we started 5 minutes later. I have 10 minutes. I will try to do it in 5. Or maybe 7. 8. But so then section 4.4, some other inequalities. So first, Blaszke-Santalo inequality. So let K be a centrally symmetric body. With respect to the origin. So that's what is usually used for the Minkowski norm. Then if we take the volume of K and multiply it with the volume of the polar body, so this is this dual body which makes out of the support function the Minkowski functional, then this product is less or equal than beta d squared. So beta d is the volume of the ball. So this is volume of the ball squared. And equality here is if and only if K is an ellipsoid. it is possible to prove this theorem by using the Steiner symmetrization. So we have all the tools that we need for that. But there is another inequality, so where one asks, let us take this product, volume of K and volume of its dual. When does it minimize? So it maximizes for the balls. When does it minimize? So there is no theorem, there is only conjecture by Mahler. So under the same assumptions, so for centrally symmetric, with respect to 0, then the product of K times, so volume of K times the volume of the dual is bigger or equal than some other constant, 4 to the power d divided by d factorial. And this is not proved. And it is conjectured that so the equality is assumed to be attained. Equality for, well, so now here the maximum is for something very round, so for ellipsoids and for the balls. So in fact this product is affinely invariant. If one transforms K affinely, then the product does not change, which is not obvious, but true. Then the minimum must be attained for something very non-symmetric. What is the most non-symmetric, I mean, non-round, I'm sorry. So here one has to be very round, here one has to be very non-round. What is the least round convex and centrally symmetric body? This is something like a cube. But equality is not only for cubes, because if here you take a cube, then the dual is the dual of the cube. This is the closed polytope. And I mean, one can exchange K and K circle here. And it turns out that the equality, at least of this constant, is attained for cubes and some other more complicated things called Hanna polytopes. So this is the result of application of products and convex hulls to segments in coordinate lines. So products, I mean Cartesian products and convex hulls applied to segments of the coordinate lines, coordinate axis. So there was quite a lot of work on this conjecture in the recent years, and it was related to symplectic geometry, to capacities in symplectic geometry, but it is still not proved. Okay, so that's it for today.